morning who are worried it's still a little too iffy. All the rest of the week, you're just doing lab as normal, okay? But I didn't want people today walking in and being all confused, all right? So just so you know, if you're still going, you don't go, you get a 0. And your lab will hopefully help fill in the concepts that you would experience, okay? As far as that lab, it includes today, because we're going to be checking pre-lab work. Remember, only parts 1 and parts 2 need to be completed. We ready? As far as our procedure, we also have to have our pre-lab assignment questions at least attempted to be answered, and pre-lab number 8 can be skipped, and that does go for today to be home along with the rest of the week. Post-lab number 3 may be skipped. We know we have a quiz on Friday. I'll know better on Wednesday what will be on that quiz, but we're going to be starting with a couple practice problems. You can anticipate something similar to that in addition to other things on that quiz. Exam 2 is Thursday the 23rd, 5:30 p.m., 60 minutes, lab 162, picking up where we left off. Section 3.6 through something, meaning picking up with finding empirical formula for precise composition information. I did quit before the Moodle Exam 1 was split to old and new. Remember, it ends with the end of chapter 3, although I did put everything up in the old. We're still covering a little bit of that material today. 1 through 100 will be graded. That is due on Friday. Don't wait till last minute to do 100 problems. But since we anticipate starting chapter 4 today, there are some Moodle Exam 2 problems that go along with the beginning of chapter 4, and so I've noted that one of them new. Wednesday they'll move to old. Any questions? Any questions? We good? All right, we said last time we were going to start up with number 14, do that practice problem. Although we had gone to that page, I am actually going to put my sheets on the center screen. In addition, I just wanted to show you all the slide is that on your little circle, which is black and white, we're going to count the particles really quick first, and then I'm going to put the sheet over, okay? So for right now, we're going to leave the slide up just so we can have that color image, and then we'll move it. So we're just going to count the particles that are in our particle diagram. I'm going to label underneath my reaction. So we have 4 ammonias reacting with 6 NOs. And this is going to produce 5 diatomic nitrogen and 6 water. As far as NH3, we know that there are 4 atoms there, 3 of which are the same. So even in your black and white, you could have probably found those. We have 1, 2, 3, 4, 5, 6 of them given to us. It's really to tell the difference between the diatomic, to tell the difference between the colors in that diatomic molecule, although you probably could have gotten by with black and white. We have 2 different atoms put together. These are only reactions here, not to be confused with our diatomic nitrogen. So we have 1, 2, 3, 4, 5, 6, 7, 8 of those guys. I wanted to make it clear as to where we got those numbers from before I took the slide away and put the dot camera in the center. Any questions on where those numbers came from? It is often a question, so it's the only reason I'm asking more than once. All right, let's put the dot camera in the middle. Maybe to zoom in a little bit too, but we're waiting for that to click in. All right, refocus, there we go. So we're given the reaction, and we have the vessel, we have our balanced chemical equation. We're asked to determine what the limiting reactant is, and we're told each symbol represents 1 mole of molecules of the substance, meaning we had 6 NH3s, that means we have 6 moles of NH3, and we had 8 NOs, that means we had 8 moles of NO. You could actually get different scaling factors, like each symbol represents a half a mole, or each symbol represents 2 moles, just like that. So it's not always going to be 1. Notice the scale note. We need to use scales to interpret the diagram in terms of molecules and then translate this to moles. That's kind of what we've done, but just as a reminder. Method for determining the limiting reactant. There's more than one way to do this. I have 2 main ways that I teach at times. We're going to use the method that I call comparing the reactants. So to find LR is my abbreviation for limiting reactant. I realized Friday I forgot to introduce that abbreviation to you. One method, compare reactants. Meaning we're going to start with 1, yes, question? I don't have my screen up anymore because and actually one specific product. Meaning for each reactant, you calculate over to like one of the products is say water, and then you do it for the other reactant, and we recall that the limiting reactant limits the amount of product. Because the reaction stops as soon as the limiting reactant is gone, meaning you're going to get two answers for an amount of product, and the one that's lower tells you the reactant used to find that number is the limiting reactant. I'm going to use the comparing reactants for this example, okay? I wanted you to see that there are more than one way to do this. So I'm just starting with the NO, just for the heck of it. We know that we have 8 moles of NO available. We're going to calculate to the ammonia how many moles of ammonia is needed. So we have a 4 to 6 ratio, meaning 4 moles of NH3 react with 6 moles of NO. Well, 8 times 4 divided by 6 would give me 5.33 moles of NH3, and that's what's needed to have those stoichiometric amounts. We need to have 5.33 moles of NH3 available in order to use up the 8 moles of NO. Well, then you look and see what you have. We have 6 moles given to us, or 6 moles available. We have more than enough. We definitely have 5.33, meaning the rest of it will be excess. That tells us that the NH3 is the excess reactant. ER is my abbreviation for excess reactant, dealing with another reactant. So therefore, the NO must be the limiting reactant. Why did I use my abbreviation? I don't know. Or LRT first. Any questions for how we determine limiting an excess reactant? You also see writing, so pausing, try to give people a chance to catch up. Now you might prefer the yes.
Can you just briefly go over how you got the coefficients in the equation?
They were given to us.
Like,
Okay, let's go
like where we got them from, like the image in our book.
Okay, you asked about the coefficients. So you talked about the amounts.
Yes, and then just like how it ties into the equation.
The amounts were gotten from looking at the picture.
Right.
Okay? So of NH3 we have 6 moles of that given to us. We have 8 moles of NO. The coefficients come from balancing. They're separate things.
Okay.
Make sense?
Kind
Kind
of.
of.
How, where did the fraction come from? Like, what
The
is that?
mole ratio, well, we have 4 moles of NH3 needed for every 6 moles of NO. So that's where our mole ratio came from.
Okay.
Okay? Does that make sense?
Yeah.
So then you gotta talk through a question a little bit. Anybody else? Now, as I was about to say, which is fine, I like the question. You may prefer the other method or a different method. There's more than 2. These are the big 2. If we had used the second method, we would have done 2 calculations, one with ammonia and one with NO. We would have gone to a product, same product, either N2 or H2O, and the limiting reactant, the NO, would have given us a smaller amount because it limits the amount of product that can be used. Now we're asked, what is the theoretical yield for water for this example? Well, the theoretical yield is the maximum amount of product that could be produced if the limiting reactant got used up. Meaning you must use the limiting reactant to find the theoretical yield. I don't want to bump that all the way up. I guess I'm going to have to zoom out a little bit. I want to keep as much of it on the screen as I can. There we go. So to find the theoretical yield, Ty, you must use the limiting reactant. So our limiting reactant is our NO. We know that we were given 8 moles of the NO in our particle diagram. Well, we're just going to calculate over to the water that we're asked to. So for every 6 moles of water that we get, we end up using 6 moles of NO. 6 moles of H2O are produced for every 6 moles of NO that reacts. And I know it's a 1-to-1 ratio, but if you get used to putting them in all the time, you don't forget. Meaning if you don't put them in when it's 1-to-1, then you forget other times to put it in when it matters. Yes?
Why did you choose the NO for the, like the A folder and the,
For this part down here or up here?
up there?
I could start with ammonia.
Okay.
It was, you pick whichever one you want.
Okay.
I don't like to always pick the first, because then students get the impression you gotta pick the first. Okay? So if we would have done it with the ammonia, we would have started 4 moles ammonia. Our ratio then would have been 6 moles of NO over 4 moles ammonia. We would have got a different answer, but it would have been, since the ammonia is the excess reactant, we would have been finding the NO over here, and we would have then compared what we needed to what was available. We would have found out we didn't have enough. And that would also close the delivery gap. So it doesn't matter which you choose. It's actually good practice to do it with the other one that you see, that you still get the same answer. Anybody else? Good? I know last time that we did go over 15, but there's a little part in 15 that is relating to this problem. I did say, I know it could be confusing, I just had an exam, that we were going to go back to 15. So 15 gave us our definition of actual or experimental yield, meaning the amount of product is actually or experimentally obtained. What does this mean that it's experimentally obtained? This is what you get in the lab, or if you're not doing the lab, this is what you're told was experimentally obtained. What is a possible actual yield for the example number 14? If the theoretical yield is 144 grams of water, a possible actual yield is anything less than 144. So I'm just choosing 100 grams of water. You could choose 143.999 repeating if you want. Anything less than 144 would be a valid choice. The reason why I have to choose a specific number, although we did briefly talk about percent yield also on Friday, the proportion of the actual to the theoretical, they do ask us in 16A to find our actual yield for this example. So again, as a reminder, and I'm going to have to push up a little bit, percents are always partial over total times 100. So our partial is going to be the actual or experimental. Our total is the maximum amount that can be produced, the theoretical, times 100. So for this particular example, since I chose 100 grams of water, we maximum could produce 144. Multiply this by 100, and we get a percent yield of 69.4%. Of course, that would change if you decided to choose a different actual yield. It's going to be one number to think about instead of 2 numbers to think about. Any questions that may have come up? I'm just kind of trying to get as much of this on here. I don't like being so zoomed out, but there we go. At least I got the reactive map. Can percent yield be greater than 100? Or should it? No. That'd be like, yes, question.
I'm sorry, I don't see where you got the 144 from. Like, I understand that it's the maximum, I just don't see where you got it from.
We were calculating using our living reactant to how much of our water could be produced.
Oh, okay.
So the amount of water that can be produced from your living reactant is your theoretical yield.
Okay.
Okay? So no, definitely percent yield should not be greater than 100. If it is, it means a mistake was made. Maybe the actual yield, meaning you're in the lab doing something, maybe you made a mistake and the weight was too big or something like that. More likely, the mistake would have been made in finding the theoretical yield. You did a calculation error. Or, another likely mistake is you flipped it. You put the big number on top and the small number underneath. But in reality, it should not be, because it's the percent of the total. Can actually yield be greater than theoretical yield? No. Just a different way of thinking about the same question. So 17, 18 are just different ways of thinking about the same idea. Any questions before we go to a new problem? Meaning I'll have to get a new sheet going. The next problem is And since I've increased the mole by a factor of 2, I now have 10 oxygen atoms. Well, if I have a diatomic and I need 10 atoms, I need half as many molecules. I've now balanced the oxygen, but increasing our coefficients over here unbalanced the nitrogens and the hydrogens. What do we do here? We double. So let's double here as well. We now have 4 nitrogens on both sides. We have 4 times 3, 12 hydrogens over here. 6 times 2, 12 hydrogens over here. We know our oxygens are balanced out because 5 diatomics gives us 10 oxygen atoms. Again, leaving the diatomic for last does help. Any questions? Okay. Now, I'm not going to draw a table for part B as you have a table. I like to write right underneath my equation. So in our particle diagram, if we look for our ammonia, meaning 4 atoms and 3 of them are the same symbol, it's kind of in the middle, not quite perfectly in the middle. So we have 1 ammonia. There aren't any others that I can see. As far as the diatomic oxygen, that would be 2 atoms of the same symbols, two symbols of the same type, put together for our diatomic. I see 1 on the right-hand side, center, and 1 lower to the left a little bit. So we have 2 of those. For NO, we're going to look for a diatomic compound with 2 different symbols put together. I see quite a few of them. 1, 2, 3, 4 of them. And our water is what's left over. 3 atoms put together, 2 of the same type. 1, 2, 3, 4, 5, 6 is what I see. So in your table, you should have 1 ammonia, 2 oxygen, 4 NO, and 6 waters. To apply the scaling factor, we just need to multiply these numbers by 1/2, or 0.5. Meaning, 1 times 0.5, I will have 0.5 moles of NH3. I will have 1 mole of water. Sorry, I don't know why I said water. Oxygen. I'll have 2 moles of NO, and I'll have 3 moles of the water. Notice, I meant to say it earlier when we were just counting particles. We have a mixture of products and reactants, meaning the reaction has started and it went to a point where it kind of stopped, but not everything got used up. Meaning we still have reactants left over. Lots of reactions do not go to 100% yield. We're asked to find a living reactant. Yes? Oh, thank you. Yeah.
How did you get 22 for the first different one? 22 for ammonia and oxygen? Okay.
I didn't hear you.
How did you get 1 for ammonia and 2 for oxygen?
We've got 1 ammonia right there, and we have 2 oxygen.
So we're just counting.
Yeah, we're just counting on here. Okay? We're going to use the reactants that are left over to figure out which one of those would have been used up first if the reaction went to completion. And again, to keep things kind of simple, I use the comparing reactants because I know it's going to be the same lecture. Okay? You of course can use a different method. I just want to confuse people by going to the other method right now. So we know that we have, where was I? Right here are, I have to rewrite this because this right here is bothering my head. So 4 NH3 plus 5 O2. This is just on my brain. 4 NO plus 6 H2Os. So here we have a mixture of our 2 reactants. We know we have both of them left over. I'm going to pick one to start with. Last time I used the second one. This time I'll just use the first one. So 0.5 moles of NH3. I'm going to calculate how much of the oxygen is needed to use up that NH3. We're getting our ratio from our coefficients. For every 5 moles of O2 reacted, you need 4 moles of NH3. So 0.5 times 5 divided by 4 will tell me I need 0.625 moles of O2. How much were we given? We were given 1 mole of O2. We were given more than enough. We will use up the 0.625 and still have leftover oxygen. That tells us that the O2 is the all got cut in half. Math. Our next step, E, and I'm sorry I didn't label them. What is the theoretical yield in mass in grams of NO? Meaning specifically, we're looking at the product NO. Remember, theoretical yield is the maximum amount produced if the limiting reactant got used up. We have to remember it's the maximum. We already have 2 moles of NO present. 2 moles of NO already produced. We need to figure out how much more could have been produced if we used up the limiting reactant. So we have to start with the limiting reactant, which we already determined was our NH3. We have a half a mole of that reactant, so 0.5 moles of NH3, bless you, times, we're going to NO, but we have 4 moles of NO for every 4 moles of NH3. Again, I would highly advise putting it in even if it doesn't change the number. Meaning, I can still produce 0.5 moles. I can produce more if the limiting reactant got used up. Therefore, the maximum amount is the addition of the 2. Theoretical yield is the maximum. 2 plus 0.5 is 2.5 moles of NO. We still have to get mass. To get it to mass, we just use molar mass for NO, which ends up being 30.01 grams per mole. This will tell us that in mass, we could have produced 75.03 grams. That is our theoretical yield. If we knew the amount of reactants at the beginning, we could have just done it like we did last time. But some of them have already been used up, so we have to think about what's already produced for that product and think of how much more can also be made. Common question is, why did you add them together? We need the maximum. Bless you. Part F wants us to find the actual yield. That's what's actually produced. That's what's being shown to you in the particle diagram. Actual yield, what was already produced? We already produced, sorry, a little messy there, 2 moles of NO. We had 4 particles, we had a scaling factor that brought that down to 2 moles. We just need to get 2 moles in a mass. 2 moles, NO, times 30.01 grams in each 1 mole, and that will tell me that my actual yield in terms of mass was 60.02 grams. This is the way you can pull the actual yield without going to the lab. You're given the mixture and you have some product there already. That's what was actually produced. Last step is percent yield. Partial over total times 100. I'm going to try to squeeze at the bottom. I'm going to move up inch. I make sure I don't have enough room. Our percent yield, which again is actual or experimental divided by theoretical times 100. In this case, that would be our small number, 60.02, divided by the bigger number, 75.03, times 100, meaning the reaction went to 80% yield. 80% of the mass was produced. Looks like some are still trying to figure it out. Any questions? You're good. I'm also leaving out something to writing down. If you look at your lecture activity pages, page 95, 96, and 97 were those lecture activity problems that I put up last time in the end of chapter At the bottom page 104 of the electroactivity book. So this stuff is in the video. That's what I want. I like to start, it's actually in the video too, but I like to start at the tail end of that video, because electrolytes is a nice place to start, because if something conducts electricity when dissolved in water or not is actually a major playing factor in this chapter. So an electrolyte is a substance that when dissolved in water results in a solution that can conduct electricity, meaning there are mobile ions. I'm going to help you kind of classify things a little bit. So, wrong screen. So an electrolyte we see the example of sodium chloride. Make sure I'm down far enough. Nope. There we go. Soluble ionic compounds definitely will produce ions when they dissolve in water. So soluble ionic compounds. We also had our definition of acid in chapter 2 as a substance that produces hydrogen ions when dissolved in water. There'll be ions there if you have an acid, so that will also be an electrolyte. Bases, we kind of know some of them, although we didn't do the definition. Our hydroxyl bases are soluble ionic compounds that have hydroxide. So I'm just going to write down bases, but when we get to the section on acid bases, we'll have a better idea of what that means. But I'd like to give you a full category list right now. Then we also have our non-electrolyte, a substance that when dissolved in water results in a solution that does not conduct electricity. We have our methanol example. Dissolved liquid methanol in water, we just turn it to aqueous. It doesn't break apart at all. Non-electrolyte, there are no ions in solution. So as far as the classification, I like to say molecular compounds that are not this. So they're not soluble ionic compounds. They're not an acid, and they're not a base. To give you a nice example, something like sugar. You put a teaspoon of sugar in your coffee or tea or whatever it is you like to drink. The sugar dissolves, but it doesn't break apart. It's not producing any ions. We're not done with the list yet, though. If we go to the next slide, or that table there in number 17, we do have something in the middle here. First, just let's look at our electrolyte. Notice the word strong is there, and then we have a second column for weak. You might be wondering why I left a big gap between those two. When you look at this grouping here, you see things that you should hopefully recognize as acids: HCl, HNO3, HClO4, H2SO4. The things with hydroxide are bases, so NaOH, BaOH2, and then we have our ionic compounds there. In the middle, when we're defining strong versus weak, don't worry, we see a couple things we recognize as acids, HF and HNO2. We also see acetic acid, where they put the H at the end instead of in the front. But then we see recognizable water, and we see ammonium. Ammonium is a base. It's not all acids and bases over here. It's strong. And we'll define what it means to be strong when we get to the acid-base section. we had the methanol example before, so alcohols, sugars, things like that won't break apart. Sorry for forgetting that. This table is on page 105. Notice what it says in red. You'll be given, when needed, on quizzes and exams from this point forward, quizzes and exams that I write. Meaning, it is not given on the final exam because it's not needed. It's only given when needed. Meaning, I strongly suggest that students get to know it. Not memorize, get to know. Because by the time it gets to the final exam, the people who write those exams, and I am one of those people, my class, by the time they get to the end, it should remember this, or should remember that. For example, on the top is soluble compounds, and you can notice there are some exceptions, but if you go across there's no exception, that means it's always soluble. Now these aren't compounds, these are ions. This is an ion and another ion get together to make a compound. Meaning, any compounds that have group 1 metals in them, Li+, Na+, K+, etc., they are always soluble no matter what. In addition, the ammonium cation paired with an anion always produces a soluble compound, meaning it will dissolve in water. All nitrates, all bicarbonates, and all chlorates, no matter what cation they're with, always produce a soluble compound. If you get the always ones kind of in your head, you'll be perfectly fine for fun. Till then, you'll always get the table when needed. I mean, by the time we get to the final, I don't think it's needed anymore, but you should know something. We can see for our last two categories on the top half of the table, halides and sulfates. Some of them are soluble, meaning in general they're soluble, but there are some exceptions. Meaning, any cation to the halides besides the ones that listed with the halide produces a soluble ionic compound. If it's one of the cations listed, then it's insoluble. For example, sodium chloride, Na+, not listed, it's soluble. Silver chloride, Ag+ is listed, is insoluble. We also have a couple classes of compounds that are generally insoluble, unless they're paired with the right ion. Carbonates and phosphates, chromates, sulfides, and hydroxides. Let's deal with the first four first. We'll leave the hydroxides last because the first exception goes to all four of those. So carbonates, phosphates, chromates, and sulfides are generally insoluble unless they've got that alkali metal cation, which is always soluble, or the ammonium ion, which is always soluble. Hydroxides are also in general insoluble unless they're containing one of those group 1 metal ions or the barium cation. Meaning magnesium hydroxide insoluble, barium hydroxide soluble. We're going to practice in number 19. Are there any questions before that? This is some of those Bruno Exam 2 problems are kind of practicing. So number 19, they want us to assign the solubility of these 6 compounds. Hopefully it won't be hard. I'll go down the column that's on the slide. I know yours kind of goes down and then over. Actually, yeah, it goes down and then over. So sodium carbonate, soluble or insoluble? Soluble, right? We have a sodium cation there. Group 1 metal ion always produces a soluble compound. Meaning, if it's going to be a soluble compound, when you dissolve it in water, you're not going to see any ions. I'm just going to write underneath our Na2CO3. It will produce a homogeneous mixture. You won't see those ions there. I'm going to just get the other beaker going. If you look at the bottom page, you can kind of see why I'm doing this. If we have an insoluble compound, it would actually sit at the bottom of the beaker. So what about lead 2 chloride? Insoluble. We have the halides there. Oh, look at that. The lead 2 ion is an exception to the general solubility of a halide, meaning our PbCl2 will not dissolve, will just sit at the bottom of our beaker. Insoluble. What about the aluminum hydroxide? I heard it insoluble. Hydroxides are in general insoluble, unless there's a group 1 metal or barium there. So yes, that one would also produce a precipitate. Something's in the bottom of the beaker. AlOH3. Next one, calcium bicarbonate. Soluble. Bicarbonates is one of those classifications out there that has nitrates are always soluble no matter what. So we have FeNO3, 2. And what about strontium sulfate? Insoluble, good. SrSO4. I know they wanted to put S for soluble or I for insoluble. You could have done that if you want. And I know in 20 they're asking you to name the compounds. It's good practice. I purposely didn't name them so you would have a chance to practice if you think you need that. Any questions? Yes? The calcium bicarbonate, soluble. Bicarbonates are always soluble no matter what cation they're with. There are more than just this. You maybe remember a solubility table from a prior book. And there are things that were, like acetates were listed in the one in the Bauer book for 100 here at UWF, and they're not here. It's not a complete list. Alright? I'll stick to things that you can find on the table. We good? Now we're going to look at a new type of representation. We mix particle level and symbolic when we're doing this chapter because to know which ions are there are important. Just having circles, like, but what ion is that, right? But we also need to depict them on a particle level. This is the image from the top of page 106. Notice it's coming from the bulk, the middle of the solution. So we're not thinking about these hydroxide ions sitting around the beaker. Okay, they're floating around. So this would kind of be our nice mixed particle/symbolic representation for sodium hydroxide. We're going to do the same thing for two of our soluble compounds. In 21, it asks you for iron 3 nitrate, what would it look like in solution, versus sodium carbonate. Any questions? In order to keep things a little cleaner, especially so that I can, well, you know what? There's not a lot of slide work right now. Still, so it's a little easier to see. I usually just do the circle part. Come on. Why didn't you flip? There it goes. So I'm just going to do the circle part that's coming out of the beaker for each of them. So this would be for our FeNO3, and this would be for Na2CO3. Well, since they're both soluble ionic compounds, they will dissociate to their ions. So for our FeNO3, we would have iron 3 plus floating around, along with some nitrates. If you're asked to do this for a particular compound, I would be looking for the ratio when it comes to grading. So for our sodium carbonate, it's going to completely dissociate to its ions, Na plus, and CO3 2 minus is what it would look like in the bulk of the solution. Any questions? If I dump those two beakers, you have beakers printed, together, what possible new compounds could be formed? Meaning we would have all these guys commingling and floating around in the same solution, and they could bump into each other. Well, if we just simply say, I'm going to have the iron 3 bump in with the carbonate, that would give me iron 3 carbonate. So if we add these two, we could get Fe. We need a 2 there, and we'll need a 3 there to have that balance, iron 3 carbonate. And we could have the sodium cation bumping with the nitrate anion, NaNO3. Forgot to put the beakers up, sorry. We did that. What's the solubility of these two compounds? Would the iron 3 carbonate be soluble? Ever insoluble? Would the iron 3 carbonate be soluble? I know you don't have your thing in front of you anymore. I'm looking at it and forgot I switched the screen. No, this guy here would be a solid, or would be insoluble. Whereas the other one with the group 1 metal there and nitrates is definitely going to be aqueous or soluble. If we write this as a reaction, FeNO3, we already determined that to be soluble, therefore it could be aqueous, plus Na2CO3, aqueous, is going to go to form these two guys, Fe3CO3, insoluble solid.